Good morning, my YouTube viewers. It's Crystal here. I'm just here this morning because I wanted to do another code review for you. And this is going to be a neural network made with numpy using the seeds dataset. I know in my last two videos I used the iris dataset, but the iris dataset is a very easy dataset to use. The seeds dataset is a little bit more complicated, and so that's why I decided to do a code review. The reason why is because there's lots of code out there for neural networks, but generally the code that I've seen when I was doing my research was for a vector, so you can predict on a vector, but I don't want to predict on a vector. I want to predict on a matrix or a data set, and quite often the code doesn't work. I've gone on to definitely two websites where they had blog posts, and one guy posted his neural network saying, "Oh, if you find any mistakes, let me know." Why are you putting code on the website when you haven't checked it to make sure it works? And another one with Saturn Cloud, and again they were just saying that they were using experimental code. Why are you putting experimental code on a website? And they said it was generated by AI. Well, there's nothing wrong with it being generated by AI, but they should at least check it to make sure it works. So what I suspect is happening with Saturn Cloud is they just have people posting code, but they're not actually coders themselves because they don't check their work, which I think is ridiculous. I mean, there's so much faulty information on the internet, and that's why I decided that I wanted to go ahead and do another code review and try to put some good code on the internet, because I did the code in Google Colab, which is a free online Jupyter notebook hosted by Google. Google Colab is a great platform to use to write code in Python. The only problem is that it doesn't really have an undo function. So if you accidentally overwrite or delete code, you can go into the save history, like this is the save history. You can go into the save history, and there's a possibility that you can retrieve your code from the save history. So now that you know why I'm making this new code review, and I did it in Google Colab, we're going to go ahead and commence with the code review. So the first thing we're going to do is we're going to import the libraries, and we're going to import pandas as PD because we are importing a CSV file, and so we have to convert it to a data frame. Then we're going to import numpy, which is a numerical computation library for Python. We're going to import sklearn train test split function, which is going to split the data set up into training and validation sets. And we're going to import matplotlib.pyplot as PLT, so you can look at the outcome, but I'm not sure it's going to be used in this one, but we'll see. And then the first thing we do after we import our libraries is we load our data set using CSV. I'm using Jason Brownlee's seeds data set. I also would like to say that I look at Jason Brownlee's website a lot, but a lot of his code is really old. Some of his code is dating back from 2016, which is 8-year-old code. And so Python has made a lot of advances. There's been lots of libraries since 2016 when he made his neural network code. And I just couldn't, when he uses lots of functions, but 2, I just couldn't use his code because it was 8-year-old code. Like it was good code, but because he uses so many functions, and he wasn't using pandas, he was using like the CSV library in Python. I just found his code really difficult to use, and he was also splitting it into folds, K folds, and things like that, and I just found it really difficult to use. So I don't know if Jason Brownlee is watching my video, maybe he can see that I couldn't use this code because it's so old and he was using really old techniques, and perhaps maybe he could update his code, or he might steal my code, you never know. So we've loaded our data set and we've converted it into a data frame, and we've called it seeds. So it has 7 features and 1 label. And so you can see here that it's an easier data set to use than some of the other data sets that I'm going to be working with, because all of the values are floats and the label is an integer. We want to see how many unique values that we have in seeds. We have 3 unique values. It's 1, 2, 3. And so X is the seeds data set and all of the columns of data except for the last one. The Y value variable is the seed data set, and it's the last column of data. So we do a value count, and so you see 1, 2, 3 have 70 examples each. We're going to convert X and Y variables to numpy arrays, and we're actually going to standardize the data. It's not normalize, it's standardize. And then, so mean X is x.mean, std.deb is np.stdx, and then so X equals X minus mean X over std.deb. Now we're going to one-hot encode the label. So num classes equals len np unique y. Y one-hot equals np unique y. So that's 1, 2, 3. Y one-hot equals np zeros, y shape, num classes. So basically what you're going to do is you're going to make a matrix of all zeros that is the number of examples in the data set with the number of classes. So it's going to be 210 by 3. Y one-hot equals np range, y shape is 0, y minus 1 equals 1. So basically, you have to make it y minus 1, and the reason why is because the seeds label is 1, 2, 3, but in Python it starts, the first number is 0, so you have to subtract 1 from that, and it says print y1hot.shape, and it's 210 with 3, and if you want to print y1hot you can, but it's going to be really long. Now we're going to split the data set into training and test sets. The first thing that we're going to do is we're going to split the X and Y1hot variables into training and validation sets. So it's going to be X train, X test, Y1hot, Y train 1 hot, Y test 1 hot, and then we're going to split it and make it a test size of 2. And then we're going to print off the shape. And you can see in the label you have 3 columns of data, whereas originally you had only 1 column of data, which is what made it 1 hot. Now we're going to split it again which you don't necessarily have to do that. There's lots of ways that you can do things, and so I went ahead and split it again to make the X, Y, and break that down into training and validation sets. But there's another way you can do it without splitting the data set a second time, which maybe next time I do a code review, I might show that. But you take X train, X test, Y train, Y test equals train test split, X, Y, test size equals 0.2, random state equals 42, and then you print out the shapes. And you can see that in this particular training and testing set, the Y variable only has one column of data other than 3. So we're going to define our module. We're going to define the sigmoid function. So the sigmoid function creates an S-curve, and that's going to be useful in this neural network, which we're going to be using. And the sigmoid derivative is a derivative of the sigmoid function. So we have to define the neural network architecture. So input neurons equals xtrain dot shape 1. So that's your number of columns or your number of features. Output neurons is num classes. That's going to be 3. Hidden neurons equals input neurons plus output neurons. So I think it's going to be 7 plus 3 is 11, I think. Initialize weights and biases. So you're going to set your seed to 42, your weights and your weights input hidden equals np.random uniform, size equals input neurons, hidden neurons, biases hidden equals np.0, 1 hidden neurons. And then let's just see np.zeros. Okay. np.zeros is the shape is 1, and then so it gives you your shape, and then data type order like. So this np zeros is shape is 1, and then it's hidden neurons. And hidden neurons I think is 11. And the thing about numpy is numpy, they give you sample code, whereas JAX, which we will be covering later, they don't give you sample code. So weights hidden output equals np.random uniform, size equals hidden neurons, output neurons, and biases output equals np.zeros, 1 output neurons. So we set our hyperparameters. Learning rate is 0.01, epochs is 1000. So now we're going to train the neural network. So we're going to set it up for forward propagation. So let's look over here for it says forward propagation. Forward propagation is a way to move the way data moves from left input layer to right output layer in the neural network. A neural network can be understood by a collection of connected input-output nodes. The accuracy of a node is expressed as a loss function or error rate. So that's your forward propagation. And it says hidden inputs equals np.dot, xtrain, comma, weights, input hidden, plus bias is hidden. Hidden outputs is sigmoid, hidden inputs. Final outputs equals np.dot, that's your dot product, hidden outputs, weights, hidden output, plus biases output, final outputs equals sigmoid final inputs. Calculate the error. Error equals y train hot, 1 hot, minus final outputs. Now we check the back propagation, and what the back propagation does is the back propagation goes back and it kind of like fine-tunes the accuracy, but we'll look it up. Backpropagation is a widely used algorithm for training feed-forward neural networks. It computes the gradient of the loss function with respect to the network weights. It is very efficient rather than naively computing the gradient concerning each weight. Okay, and then so output error term equals error times sigmoid derivative final outputs. Hidden error equals output error term dot that's your dot product weights hidden output t. The t means it's transformed. Hidden error term equals hidden error times sigmoid derivative hidden functions. And now we update our weights and biases. Weights hidden output equals weights hidden output plus hidden outputs dot t dot output error term times learning rate. Biases output equals biases output plus biases output NP sum. Output error term axis equals 0, keep dims equals true times learning rate. Weights input hidden equals weights input hidden plus x train dot t dot hidden error term times learning rate. Biases hidden equals biases hidden plus np dot sum hidden error term axis equals 0, keep dims equals true times learning rate. So that's your training process. And then what we're going to do is we're going to test the neural network on the test data. So hidden layer input equals np dot x test weights input hidden plus biases hidden layer output equals sigmoid hidden layer input output equals input np dot hidden layer output weights hidden output plus biases output. Predicted output equals sigmoid output. And then so what's going to happen on the predicted output is going to give you a matrix of the number of rows of the test data with 3 columns of data, and each column of data is going to have a float. And then so what we have to do is we have to convert the 1 hot encoded predictions to class labels. Predicted labels equals NP argmax, predicted output axis 1. So the argmax, what it does is it takes the row of data and it selects the particular column that it's in that is the largest. Predicted labels equals predicted labels plus 1, because remember at the beginning of the program you had to subtract 1 from it to get it to work. So because at the beginning of the program you subtracted 1 from it to get it to work, at the end of the program you have to add 1 to it to get it to work. And it says print predicted labels. You can see the predicted labels, and then it says print y-test, and you can see y-test. So y-test is your actual labels. Calculate the accuracy. We've got a function to calculate accuracy, and we had accuracy of 90%. And then we have another way to calculate accuracy, because I was having some difficulty doing this, so I calculated the accuracy 2 ways. But I've got 2 ways that you can calculate accuracy, and you can use the way that you like best. So now what we're going to do is we're going to compare the output that we got from the homemade neural network to sklearn's MLP classifier, and we got an accuracy of 92% on when we use sklearn's MLP classifier. So that means sklearn's MLP classifier performed better than this homemade classifier, but nevertheless, it's still a good idea to know how to make a classifier and to study the code of classifiers. And the reason why is because, just because you just need to know the theory of doing it. Anyway, so it didn't, if I knew better, if I had better code and I was more skilled at making neural networks, then perhaps I could use the code that the people in sklearn used and get my output as good or not better than the output from the people at sklearn. But at this point in time, my skill level is not as good as the skill level of the people in sklearn. So that's it. That's it. We've covered all of it. And so what we're going to do is I'm going to go ahead and close this video. And the reason why I'm going to close this video is because I've covered the code review in over 20 minutes. So I would like to thank all of my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. If you want to be notified whenever I make a new video, please tap onto the bell button next to the subscribe button. And thank you so much for watching my code review. I look forward to making more code reviews for you in the future.